First thing, what is radioactivity? You may have heard about radioactive emissions, alpha, gamma, nuclear explosions, mutations. All of this, they are radioactive materials, okay? Radioactivity. So what is the main cause of mutation? If you have watched there's one very famous movie, the Chernobyl. I'm not sure if you have watched that one. That one is like talk about the nuclear reactor explosion, right? Like back in, I forgot what is the year already. Like back in, like there was one accident about the explosion of the nuclear reactor. You know the nuclear reactor, right? The power plant where they generate electricity using nuclear radioactive materials like uranium. And then one day it got uncontrolled and it exploded. Okay, exploded, and then the whole region became unpopulated for decades. It's because of the radioactive materials staying there like almost like forever. Okay, you have to wait like decades, centuries for all the radioactivity to kind of like disappear lah. But we are not even sure if they can like completely eradicate all this radioactivity. But the thing is that after the explosion, right, all this radioactive material, they stay in the air, in the atmosphere, right? So if you happen to be in the region where this happens, right, it can kill you in minutes, in days. It can kill you in days. So that is the danger of radioactive materials. When you are exposed to radioactivity, and then you will have symptoms like the skin will change, all that, your cell will damage, everything you have seen in the movie, right? Okay, so it's like after a few days, then depending on the dose you are exposed, if high dose, then they can kill you in days. Okay, so that is the radioactivities. Now, but here we are going to study what is radioactivity and what are the things that we need to know about radioactivities. Okay, so let's start with defining. Okay, now spontaneous process. Radioactivity is a spontaneous process of an unstable nucleus emitting radioactive emission in order to become stable. Now, what does that mean? This sentence can mean a lot of things. Let's start with spontaneous process. Okay, what is spontaneous process? Spontaneous process, there are three things. Three things. First is it is unpredictable. Unpredictable, that means that you cannot predict when it happened. The radioactivity, right? The radioactive material, they give out emission, they give out radioactive wave, we call it like gamma or alpha, right? All this they give out from time to time. We don't know when will it happen. Okay, it can be today, it can be tomorrow. Okay, so they can give out the radioactive material anytime. So that is we define as unpredictable. We cannot predict when it will happen, right? So the first one, unpredictable. And the second one, the second meaning of spontaneous is random. Random, it is a random process, meaning that you don't know which atom will give out the emission. You have, for example, like you have uranium. For example, like you have uranium made of many atoms, right? Made of millions of atoms. So let's say you have like, you don't know which atom will decay. Because in radioactivity, right, atom, they will decay and they will decay into a smaller nucleus. At the same time, they give out radiation. And these radiations are dangerous one, right? So you don't know which atom will decay. It could be this atom, it could be that atom. So it's random. Okay? It's random. So that's the second meaning of spontaneous. And the third meaning of spontaneous is It is uncontrollable. Okay, uncontrollable means that you cannot speed up or slow down the reaction. Unlike in a chemical reaction, you can add catalyst, you can increase the temperature to speed up the reaction, right? But in radioactive reaction, you cannot control it. You cannot speed up, you cannot slow down. So all these three together, we say it is a spontaneous process. Okay, unpredictable, random, and uncontrollable. So radioactivity is a spontaneous process of an unstable nucleus. Okay, here, unstable nucleus, not unstable atom. What happens if the atom become unstable? You see, here I have an atom. What happens? How do you know whether an atom is stable or not? How do you know? In your chemistry, you look at the electron arrangement, right? Electron arrangement. For example, like sodium. Sodium, you have 281. So you have one valence electron at the outermost shell. Okay, that's for sodium. And if you compare to neon gas, inert gas, okay, 28. Which one is more stable? You look at the valence electron, right? This one is octet. Stable octet arrangement. This one is not as stable as this one, right? Because there's one valence electrons. Okay, so if it donates one, then it becomes stable. So we look at the stability of an atom based on the electron arrangement. But in radioactivity, we are not talking about the stability of an atom. We are talking about the stability of a nucleus. Okay, so we zoom in, we go inside the atom. Inside the atom, so we have a nucleus, and then we have the electrons, right? Electrons like this. Okay, so we focus on the nucleus. The stability of a nucleus is the radioactivity. Okay, so how do we know whether nucleus is stable or not stable? That is the question, right? Now, just to give you an idea, how small is the nucleus? If you think about KLCC tower, okay, KLCC tower is like the atom, is like the size of the atom. And if you compare to a tennis ball, the tennis ball is the nucleus. Okay, so it's very small. The nucleus is very small compared to the size of the atom. Okay, if the KLCC tower was the atom, then a tennis ball is the size of the nucleus. Okay, it's very, very small. So because the nucleus is very small, right? So what is inside the nucleus? We have proton, we have neutron, correct? So because the nucleus is very small, so if you have two protons inside, what happened to the two protons? They will repel each other because proton has positive charge, right? So positive and positive, they can repel. And here is inside the nucleus, right? Let me draw a dotted line here, shows the inside of a nucleus. If you have got two protons, then these two protons will repel, they will collapse, meaning that the nucleus will collapse. It's because of the two same charge, too near to each other. All right. Now, that is why we have neutron. That is why we have neutron. Why we have neutron in the nucleus? Because to stabilize the force of repulsion. If I have a neutron here, then it's kind of like neutralized. Neutron has no charge, right? So if you have two proton, right, then you got two neutron to balance up. So it can hold the proton together and thus making it become stable. Okay, this is stable. Electron is outside, right? It's outside. Here we are looking at inside the nucleus, inside the nucleus. Okay, so how do we know whether a nucleus is stable or not stable? We look at the number of proton and the number of neutron. I repeat, we look at the number of proton and the number of neutron to tell whether it is stable or not. If the number of proton and the number of neutron are the same, then that is stable nucleus. Okay, because if you have two charges positive, then you need two neutrons to balance out. If the number is not the same, then it will become unstable. What happens if the nucleus become unstable? Okay, we'll talk about more of that later. Okay, now first we have to know how to see whether it is stable or not. We look at the number of neutron and proton. That is why you see in hydrogen has got only one proton. There's no neutron, right? So in the nucleus of hydrogen, just one proton. How come only one proton? Because only one, right? So it won't repel with, there's no other proton for it to repel. So just one, so it is stable. Okay, so it doesn't need a neutron, okay, because there's no repulsion, right? So hydrogen has only one proton. Now, if you look at helium, okay, this is hydrogen gas, right? Hydrogen. If you look at helium atom has got two proton inside the nucleus. It got two proton and then got two neutron as well. Okay, two proton, two neutron. Now, this is the best arrangement, meaning that you got 1-to-1 ratio. Okay, two proton, two neutron is 1-to-1 ratio. This is the most stable one. Okay, so this is stable. So helium is a stable gas, okay, because it has got two proton, two neutron. The neutron balance out the force of repulsion. Now, sometimes you have isotope, right? What is isotope? Isotope, the proton number is the same proton, but different number of neutron. That is isotope. Okay, you have isotope, for example, helium's isotope, right? So same number of proton, meaning that it has got two proton, and let's say we have tritium. Tritium is an isotope of sorry, that is for hydrogen. That is for hydrogen. Tritium is isotope for hydrogen. So let's say we have an isotope is two proton and a three neutron. 1, 2, 3. Is this stable or not stable? This will become unstable. Even though you have one extra neutron, still it can make it become unstable. Just one, it is enough to make it unstable. Okay, but in some cases it can be stable as well. Okay, so plus one, sometimes it can be stable, it can be unstable, but if you got two extra, then definitely it will be unstable. Okay, so 1-to-1 ratio is the best one. For example, like sodium 23 and sodium 24. Sodium 23 has 12 neutron and 11 proton in the nucleus. Is it stable? Sodium 23 is considered stable. Okay, even though you can see one extra neutron, but still counted as stable for sodium 23. But sodium 24, the isotope, same number of proton, 11 proton, but how many neutron it has? It has 13 neutron. Extra 2 neutron. It is enough to make sodium 24 become unstable. Okay, so sodium 24 is an unstable nucleus. Unstable nucleus means that they are radioactive material. Okay, they are radioactive material, because what is radioactivity? Spontaneous process of an unstable nucleus emitting radioactive emission in order to become stable. They want to become stable. Okay, they want to become stable. So when atom is unstable, what happened to the atom? Now, mind the words, I'm talking about atom, not nucleus. When atom become unstable, they want to form bonds, correct? Right? Form covalent bonds, ionic bonds, they donate the valence electrons. Okay, that is what they do when they become unstable. How about when nucleus become unstable? If the nucleus become unstable, then they will give out radiation. They will emit radiation. Okay, so the reason why they do this is because they want to become stable. At the end of the day, what they do here is, the purpose is they want to become stable. Become stable. This one is the same. They emit radiation. Why? Because they want to become stable. Okay, now here we talk about radiation, right? Emit radiation. What is the radiation? How many types of radiation are there? What is actually radiation? You have heard about radiation from your phone. Do not sleep with your phone beside. Okay, do not too near of the computer screen. Anything has radiation, right? What is really radiation? Radiation is just waves, electromagnetic waves, right? But the dangerous one. Okay, how many electromagnetic waves? You have like the 7, right? The 7 radio, microwave, they are all radiations. Gamma, X-ray, all radiations. But there are the difference in the danger of the radiation. The higher the energy the wave has, the danger, the more dangerous it is. Like the gamma, the X-ray, right? Going to from the left of the spectrum, go to the right of the spectrum, the frequency increase, correct? So when the frequency increase means that waves at the end of the spectrum has more energy. What happens if they have more energy? Why more energy is more dangerous? Why? Because more energy, they can give energy to your body cell when they pass through your body. When the radiation pass through your body, they can excite your cell, okay, the atom, the electrons in your cell, by giving it energy, because they have enough energy. They have so much energy, they can excite the electrons in your body cell when they pass through your body. So what happens is that when they excite the electron, they can knock off the electron, right? So for something like this, this is the atom, this is the nucleus. Then you have electron here. When I have enough energy, I give the electron, then the electron can escape, right? When they escape, what do you get? When electron escape from an atom, you get ion, because now it has less electrons, so it becomes a positive charge, right? It becomes a positive charge. So these are ion. From atom become ion. Who is making it become ion? The radiation is making it. Okay, the radiation is converting the atom to ion. Is it good or bad? Ion, another term, they are called free radicals in your body. Free radicals, it is the main cause of cancer. Free radicals. If your body has too many free radicals, okay, this is the main cause of cancer, tumor, is because of free radicals. Okay, you have studied about this one in your chemistry, in your physics, all that. Biology also, right? Okay, so that is why radiation is very dangerous. Okay, of course, that you got the low energy radiation, you got a high energy radiations. Okay, that is where the mutation, all these words come from. It's because of the change in the cell, in the body cell. Okay, from atom to ion. Okay, now, so we talk about radiation and the danger of radiation. Now we look at how many types of radiations in this chapter that we are going to talk about. When a nucleus becomes unstable, it gives out radiation in the form of 3 radiations. First, we call it alpha radiation, and then we have beta radiation, and we have gamma. Okay, you may have already familiar with gamma, right? This is the waves, but alpha, beta, okay, this is wave, electromagnetic wave, but these 2, they are particles. This is a particle, this is also particle, meaning that they have mass lah. If a wave, then it doesn't have mass, it's just energy. So alpha and beta, they are particle, and gamma is a wave. So all these three types of radiation, we short this as alpha, beta, and gamma, like this. Okay, now what happened when the nucleus emit radiation? Initially, they are what we call the parent nucleus. Okay, parent nucleus, they are unstable. For example, like our sodium. Where's our sodium? Our sodium 24, unstable. Okay, now once they become unstable, they give out radiation, right? When will they give out radiation? You don't know, right? Because spontaneous process. You don't know when. It can be random. It is uncontrollable. You don't know when, right? So once it gives out radiation, so you got alpha, you got beta, you got gamma, and then it becomes a daughter nuclei. Okay, you will see this word keep appearing. A daughter nucleus, or plural form, a daughter nuclei. Okay, because sometimes one parent nucleus can break down into a few smaller daughter nucleus. Okay, so not just one. And then once they become daughter nucleus, daughter nuclei, they become stable. Okay, stable. So all this just to achieve stability. And remember, here we are talking about nucleus, okay, not atom, inside the atom, even smaller. Okay, so that is for radioactivity. Now let's go to the next part. We will study these three types of emissions one by one. Okay, now you can take a screenshot of this and I will go to the next slide. Oops. Okay, next one, we look at the three types of emissions, right? So first, let's start with alpha. Okay, you should be seeing the picture. Alpha, what is alpha? Now, alpha is the nucleus of helium. I repeat, alpha is actually the nucleus of helium. The nucleus of helium has two neutron and 2 proton. Okay, so I label like 2n, 2p. This is the nucleus of helium. We call it alpha particle. It is a particle, it has mass. Okay, so the symbol is this one, He42. 2 neutron, 2 proton. Okay, remember this is the proton number, right? This is the proton number. And what is this? The 4 is the mass number, the nucleon number. This is the number of proton. This is what? This is proton plus neutron. Okay, proton plus neutron, 4. So meaning that if you take 4 minus 2, you got 2 neutron. Okay, 2 neutron, 2 proton. That is alpha particle. Now, alpha particle, it is a positive charge. And it has a charge of 2 plus, which is quite higher because the charge of 2 quite higher, the charge 2 plus. Now, because of the high charge, right? So it is most strongly ionizing. What is means by ionizing? Ionizing is the ability of the particle to make the atom become ion, just like the one that we talked about. Okay, so you have the nucleus, you have electrons like this. So what happened is that when the alpha particle pass through nearby, because its charge is very strong, 2 plus, it can pull the electron out from this atom, right? So this electron got attracted by the alpha particle. When it goes nearby, pass by, then this electron got pulled out. What happened to this atom? This atom will become an ion, right? Because now it loses one electron, it becomes positive. This process, the process of pulling the electron out and making the atom become ion, we call ionization. Okay, ionization. So alpha is most strongly ionizing of the nuclear radiations. Can you guess why? Because of the high charge, 2+. That makes it the most strongly ionizing. Okay, now next one, you see least penetrating. What is mean by least penetrating? I mean that it cannot pass through, so it cannot travel too far. Okay, sorry, it cannot travel long distances. Least penetrating. The moment it is emitted, the moment alpha particle is emitted, a few centimeters gone already, disappear, die already. Why? Because it has very high charge, right? The moment it is emitted, right, it will interact with the particle surrounding. It will give up its energy to interact with the particle in its surrounding. Okay, so that makes it travel only very short distance. Okay, very short distance. So it cannot go very far. So we say that it is the least penetrating. Penetrating means pass through, something like that. Okay, pass through. Right? Now the range in air of the alpha is only a few centimeters. Okay, so what is emitted? A few centimeters, then the alpha particle is gone already. Okay, so and can be stopped by a thick sheet of paper. How do you stop alpha particle? You just take thick sheet of paper, like the A4 paper, you take a thick sheet, and then you can stop alpha particle from going through. Okay, so that's for alpha particles. Now I want you to remember the symbol. All right, the symbol, we use two symbols. We use either this one, 4,2, and then we write He. Why we write He is because it is the nucleus of a helium, right? Alpha is the nucleus of helium. That's why we write He. So this symbol shows the nucleus of helium. And then you can either write this or you can write alpha. Both are okay, are acceptable. All right, let's go to the next one. The second one, the second emission is the beta emission. Now, beta, what is beta? Beta is electrons. All right, beta particle is high-speed electrons. High-speed electrons. When the electrons are emitted, they travel at very high speed. Okay, so they carry negative charge. Why? Because they are electrons. Okay, what is the charge? -1. -1. Okay, so because the charge is less than the alpha particle. What is our alpha particle? Our alpha particle is 2+, right? So our electron is only -1. So the charge is less, so that is why they are much less ionizing than the alpha particle. Okay, now if they are less ionizing, then they are more penetrating, because less ionizing means that they interact less with the surrounding particle, so they can travel longer. So they are more penetrating than the alpha emission. Have a range of a meter or so in air, okay, a few meters, and can be stopped by a few millimeters of perspex or aluminium. Okay, perspex is like the car plate. The car plate number, okay, is made by perspex, okay, and also or aluminium. Aluminium, you can use that to stop the beta particle from penetrating. Okay, so what is beta again? Beta is high-speed electrons. Okay, high-speed electrons. So electrons is way lighter than alpha particle. Beta particle is very light, lighter than the alpha particle. So alpha is heavier. Okay, so the symbol for beta particle, this one, you have to remember the symbol E0 and then -1 here. Okay, And or you can write beta as well. Right, next one. Next one is gamma. Is gamma a particle? No, it is not a particle. So gamma has no mass. No mass. What is it? It is a wave, meaning that it is energy. When gamma is emitted, only energy is emitted. Okay, so often emitted at the same time with alpha or beta particle. They are the least ionizing. Why they are the least ionizing? Because they don't have charge, right? Don't have charge, unlike the electrons and the alpha. Okay, one is 2 plus, one is minus 1. So they are the least ionizing of the nuclear radiations, but they are the most penetrating. Okay, so the wavelength is very small, right? So the gamma is like the end of the spectrum, right? You have the spectrum here. This is the last one, gamma. What happened from left to right? Frequency increases. What happened to the wavelength? The wavelength decreases. So the smallest wavelength is the gamma. Okay, because of the smallest wavelength, it can pass through many objects. Nothing, not nothing lah. Almost many objects they can pass through. Okay, it's very hard to block it. It's because the small wavelength. Okay, so they can travel at very focused beam like this. Okay, now most penetrating, their intensity is greatly reduced by several cm of lead. Okay, lead, lead is from the periodic table Pb. Okay, lead. So lead is a very dense material. It's a very dense, meaning that the particle is very close. If you take one volume, 1 centimeter cube, the particle is the mass is very high, means that there are more particles in 1 unit volume. So because of so dense, because of the high number of particles, so they are able to block the gamma ray. Okay, so the gamma ray pass through. Can it block 100%? No, it cannot block 100%. It's only block about like 90%. Okay, 90%. Maybe only left like 5 to 10% that can pass through. We can never block 100%. Okay, there's still certain amount left for the gamma to pass through. Right? So why we use lead is because it is very dense material. Okay, so but they are never completely absorbed. Okay, so we already say about that. So that is gamma ray. Now, 3 types of emission. When will they come out? When the nucleus is unstable, they want to achieve stable. They give out these 3 emissions. It can be 2 at the same time, it can be 3 at the same time, or it can be 1 at the same time. We don't know. Okay, we don't know, we never know. Right? Now, this is for the nucleus. Atom, when they are unstable, they do what? They form bond to become stable. Okay? Now, next one, we will look at what are the characteristics of the properties of the emissions. Okay, let's look at the first one. Oops, sorry. Okay, this one first is ionizing characteristics. Which one is the most ionizing? Alpha, right? Because it has the highest charge. So when the alpha particle passes through, you can see it pulls the electron out. It pulls the electron out, and these atoms, initially they are neutral. Now they become ion. This process is known as ionization. Okay, so alpha particle tends to attract electrons away from nearby molecules and cause the molecule to become ion. So this is one of the reasons why alpha particle, they travel short distance. The moment they come out, they give out all the energy to the nearby particles. So alpha is the most ionizing, followed by beta and then gamma. Next one, penetration power. Which one is the most penetrating? Gamma is the most penetrating, followed by beta, and then the last one is alpha. Okay, so the penetrating and the ionization power is like completely opposite. If you are the best ionizing, you are the worst penetrating. Okay, you are the worst penetrating, you are the best ionizing. Okay, so how do you stop alpha particle? We use paper, we can stop it. How do you stop beta? We use perspex or aluminum, right? But gamma, we have to use lead. Get lead to stop it. Okay, the effect in the electric field. Electric field, current. Here we have negative charge plate. At the bottom, we have positive charge plate. So alpha, because alpha is positive, right? It is positive, so it will get attracted to the negative. That's why it curves like this. Beta is a negative charge, it's electron, so it will get attracted by the positive plate. But why is the electron more curved than the alpha here? The reason is because of the mass. Okay, the electron has very low mass compared to the alpha, so the curvature is more. Gamma, no charge, so it can go straight through like this. Gamma ray is neutral, it is not deflected. Okay, in the exam, they will ask you, they give you all these three trajectory. They ask you, okay, what is this? What is this? What is this? Okay, those straight line is the easiest one, gamma source. Okay, attracted to negative is the alpha. Okay, this is for the effect of the emission in electric field, right? The next one, we look at magnetic field. Okay, so let's go to the next one. Here we have magnetic field. The one labeled X. What is the X? Into the page, right? Into the page. So meaning that the magnetic field is pointing into the screen. Right now, you're looking at the screen, is pointing to the screen. All right, so alpha particle, they are positive charge, right? Positive charge, when they flow in the magnetic field, the velocity is moving to the right. What is the current direction? Current direction follow positive charge. So if alpha particle is moving to the right, then there's a current to the right as well. Okay, so there is current form because there's flow of charge. Current is flow of charge. So alpha particle flow, current will flow same direction as the alpha particle. So we use our Fleming's left hand to find the force directions, right? So your index, you point to the screen, 你的食指指去那个 screen， 你的中指指去右边，因为你的中指是 current 嘛，对不对？ Current, so current is to the right, so you point to the right, and then your thumb is upward. That is why the alpha particles curve upward, is because the force acting on a particle is upward. Okay. Now gamma, very easy, straight. That's gamma. How about beta? Beta is electron, is a negative charge. So when it enters the field, it is moving to the right also. But what is the current flow? Remember, current and electron, they are opposite direction, right? So the current is to the left. Again, we use our Fleming's left hand. Your middle finger point to the left. Your index point to the screen. What do you get? You have to twist your wrist a bit. Okay. So you get your thumb pointing which direction? Downwards, right? Downwards. So the force produced is downwards. This produced is upward. Why is it more curved? Because of the mass. So this is the effect of the emission on inside a magnetic field. So magnetic field, you have to do the Fleming's left hand. Why we use Fleming's left hand? Remember, I said about wear your watch on your left hand, right? Your watch got current. So whenever there's current, we use left hand. No current, we use right hand. That is for the generator. Okay. Next one. Go. Erase this out. Oops. We go back to the board. Okay, let me go back to the board. Okay, this is next one. We will talk about the alpha, the decay process. Okay, so we got alpha decay, we got beta decay, and we got gamma decay. Okay, let's start with alpha decay. During alpha decay, what happens to the atom? This is the nucleus. Okay, let's say we have an atom of AZ, a random atom with AZ, okay, nucleon number and the proton number. The decay process, we draw an arrow. After it give out alpha, it become what? Now, what is alpha particle again? It's the helium nucleus, right? So He42. When it give out one alpha particle, that means A -4, Z -2, and it become a whole new atom. I label it as Y. It is not the same. It's not the same anymore because the proton number has changed. So it becomes Y and then plus the He that is emitted. This is the equation for the decay. You have to remember this equation. Okay, so let's say example, we have 212, 92. After alpha decay, this one 212 we -4 become 208, 92 we -2 become 90, and maybe we use Y. Plus 42 He. Okay, another example for you. So make sure that both sides are balanced. So 212 here, make sure here add up to this one, you get 212. Same for this one, 92, 90, and 2. Okay, an example would be uranium. Okay, uranium 238 and then 92. Decay by giving out alpha, become thorium. Guess what is the number here? -4, right? 238 we -4, 234. This one becomes 92, becomes 90. Okay, so plus, and then you put the alpha particle, He42, or you can just put alpha like that. Right, so when you see this, then you know this is alpha decay. Decay means like give out, alpha decay. Okay, now, do you have to remember this one? No, you don't. You don't need to memorize. You don't need to memorize like uranium, okay, become thorium, no need. Okay, no need. You just need to know the general equation, how to write it. Okay, because they will ask you to write it. But for this one, uranium to thorium, you don't need to memorize. Another one is like polonium, 21084. Decay become what? Become lead. Okay, do you need to remember this? No, no need. Okay, they will give you this. Maybe they will ask you to only fill in the nucleon number and the proton number. Okay, so 210 minus 4, we get 206, and we get 82 here, plus 42 alpha. Okay, so that is alpha decay. Now, next one, we look at beta decay. Beta decay, means that give out high-speed electron, right? Electron is 0, -1. Okay, what is happening during the beta decay? Now, inside the nucleus, let's say this is the nucleus. Okay, we got neutron and proton. Let's just take an example. So let's say that this one decay, this nucleus decay. So what is happening is that one neutron, let's take one neutron out. One neutron will break down, and it will break down and it will turn into one proton and one proton and one electron. Okay, so this neutron will break down into one proton and one electron. Okay, so meaning that you get two things, right? Two things out of it. You get electron and then you get proton. Now, what happened to the electron? The electron will be emitted. It will leave the atom. You will completely leave it. Okay, emitted. That is the beta. This is the beta. Okay, so this is the beta. That's why you get beta emission. Traveling at very high speed. Okay, high speed. Now, how about the proton? The proton will stay in the nucleus. Stay in the nucleus. Only the electron is emitted, right? So what do you get as a result? You get this one become, initially you got how many proton? 2 proton, right? 2 proton, and you got 3 neutron, right? 3 neutron here. So now become 2 neutron and then 1 extra proton. Because 1 neutron already break down into proton and electron, but the electron already escaped, already leave the nucleus. So end up having 3 proton here and 2 neutron here. Okay, so this is what happening in the nucleus during the beta decay. Okay, now let me ask you a question here. What happened to the nucleon number? Nucleon number. The nucleon, okay, nucleon number. What is nucleon again? Nucleon is the proton plus the neutron, right? It is the number shown up here, the A. The Z is the proton, right? What happened to the nucleon number when this occurs? Initially, we calculate how many nucleon number? 1, 2, 3, 4, 5. 5. After that, how many nucleon? 1, 2, 3, 4, 5. 5. Same. Why is it the same? Why is it not different? It's because even though 1 neutron already become proton, right? But it's still the same thing. It doesn't affect the amount of nucleon number, right? The electron leave the nucleus, but this neutron change to proton. Still doesn't affect. It still doesn't affect the nucleon number. That is why the nucleon number is the same. This one is very important. You need to remember. Okay, so in the beta decay, there is no change in the nucleon number. Okay, no change in the nucleon number. So meaning that this one, I can write the equations. I can write TH, oh, sorry. We start with Z, sorry, X, AZ, decay, this is beta decay, and then into Y, okay, we get a different element, but the A is the same, right? AA, but this one, Z, what do? Guess what? We plus 1. Why is it plus 1? This is proton number, right? Because 1 neutron has changed to proton, right? Remember this, 1 neutron changed to proton. So you got 1 extra proton here. That is why we plus 1. After the decay, you plus 1. This is the proton extra from the breakdown of the neutron. Okay, and then we plus the electron 0 minus 1. Make sure it's balanced. Is it balanced? A 0. Okay, it's balanced. Z 1 minus 1. It's balanced. So this is the equation for the beta decay. For the alpha decay, this one. Okay. Now the beta actually got two. This is the overall one. We got another one equation is for the inside the nucleus, the breakdown of the neutron. We can write it as neutron. Okay, neutron is 1 0. Okay, so the nuclear number is 1, but the proton is 0. So 1 0, we draw an arrow. We write proton plus electron. Proton is 1 1. Okay, 1 1. Electron is 0 negative 1. So again, balance. This process shows what? The breakdown of neutron in the nucleus. The breakdown of neutron in the nucleus. Okay, so these equations followed by these equations. So in beta decay, you got two equations you need to remember. All right, examples. Thorium, TH, 23490. Decay, beta decay into polonium plus beta particle. Okay, what is this number here? The nuclear number does not change. So 234, and the proton has one extra, plus 1. So it's 91. Another example, lead 21082 beta decay into bismuth, Bi plus beta particle. Okay, so this one is 210, nucleon number does not change, and the proton number plus 1, 83. Okay. The last one. We have our gamma. Gamma emission. Okay, so we don't say gamma decay because gamma is the wave is being emitted. So gamma emission, now gamma is the easiest one because gamma is just energy, right? So we have the element AZ. After gamma emission is still the same atom, all right? Same atom, same proton number, because gamma is no particle, it is just energy, so plus gamma. So everything the same, then you know it's gamma. Here. Okay? Because no change is because it is just energy being released, meaning that the nucleus will lose energy. Nucleus, it only lose energy. Okay? Now, normally this gamma, right, they come out like in packet. You say like packets. You can think of it like a packet of energy, like a lump. 好像一罎这样子，一罎 energy 这样子射出来。A packet of energy. This is how they are emitted. Okay, a packet in the packets of energy that we had another term for it. We call photons. Photons. Okay, what is photons? It is a packet of energy. Okay, so that is for gamma emissions. Okay, now there is another, out of these three, guys, out of these three, there's another emission. It's called the neutron. Because sometimes neutron can be emitted when the nucleus breaks down. Okay, but the most common one are the alpha, beta, and gamma. On top of that one, on top of these three, neutrons sometimes can be emitted. Okay, it is emitted by radioactive material. Radioactive material, like the breakdown of uranium. Okay, it will release neutron, uranium. Now, neutron has no charge. The thing about neutron, neutron is a special one. The special one. Why is it special? Is because it has no charge. Now, since it has no charge, means that neutron can enter the nucleus of any atom. You see, you see, this is the nucleus. Let's say we have an atom here. This is the nucleus, and this is the electron shell. Okay, you have many electron shell. Now, electrons are negative. So you have negative outside, but the nucleus is positive charge, right? Because you have proton in the nucleus. So outside is negative charge, inside is positive charge. When you have a proton coming, like a positive charge particle coming, can it enter the nucleus? Cannot, because it's positive charge inside, it repels positive. You cannot enter. Maybe you can pass through the electron shell, but you cannot enter the nucleus. How about if a negative charge particle is coming? Okay, at first we have proton coming, then we have a negative charge particle coming. Can it enter the nucleus? Cannot, because it is repelled even before reaching the shell, right? Because the shell is negative. Now, so neutron is a special one because neutron has no charge. So when neutron comes here, nobody will repel the neutron, right? It can go straight into the nucleus. It can enter the nucleus. Okay, what happened after the neutron enter the nucleus? Then the nucleus it got one extra neutron. For example, let's say initially you got 2 proton, 2 neutron inside the nucleus. And then you have a random neutron flying towards it. And then it enters the nucleus. What happens is that you get +1. So the total neutron in the nucleus become 2 proton and 3 neutron. Right? You got 1 extra bonus. Okay, so what happened is that when one neutron entered the when one neutron enter the nucleus, it will cause the nucleus to become unstable. Again, why is it become unstable? Because the number of proton and the number of neutron now is not the same. Before this, it was the same, 2p, 2n, but now it's 3n. 1 has been added, so it becomes unstable. Okay, so meaning that a neutron, it has the ability to make an atom become unstable. I repeat, a neutron, it has the ability to make an atom become unstable. Okay, once it enters, then the number are imbalanced, then it becomes unstable. So I write it down here, guys. Write it down here. It is emitted by radioactive material, and it can make an atom become unstable. What happens when the atom becomes unstable? Then the atom again will release emission. So this keeps on continuing. One neutron goes in the atom, make it unstable, then the atom release. Release neutron again, the neutron go to another atom, make it unstable, make it release again. That will be discussed more detail in the next lesson next week. That is something to do with the nuclear reaction. Okay, the chain reaction, nuclear. That is how you get nuclear explosions. Okay, nuclear bomb, all that is because of this one. Okay, but this one we save it for later. Okay, we save it for later. So now you only need, we only talk about alpha decay, beta decay, gamma emission, and also the neutron emissions. Okay, all right, guys. You want to take some notes? You can take some notes. Take a screenshot, and we will have our 3-minute break as usual. And we'll come back and continue. So 8:10. 8:10 we'll come back. I'll give 5 minutes, okay? 5 minutes. So 8:12. 8:12. Okay, guys, we will continue. Huh? Maybe another 20 minutes or half an hour, lah, then we'll finish. Okay. So the next part, half-life. All right, so half-life, what is it? Rate of decay and half-life. Okay, let's look at the definition. The half-life of a quantity subject to an exponential decay is the time required for the quantity to decay to half of its initial value. Okay, what does that mean? Right, the half-life, or denoted as T half, okay, T, okay, it should be a lowercase t. T half is the timer, it is timer, time takes for the radioactive substance to decrease to half of its original amount. Now, how do we measure it? There are three ways you can measure it. Let's say we have sodium. Okay, let's say we have sodium 24. Okay, sodium 24 is radioactive, right? It's unstable, so it can give out radiation. So let's say we have sodium 24, and then we measure the mass, 20 gram. Initial mass, 20 gram. And not only we measure the mass, we measure the number of atom, number of sodium atom. And we found that 5 times 10 to the 23 atoms. And then also we measure the activity. What is activity? Activity is how many emission in 1 minute. So let's say it is 200 emission in 1 minute, meaning that in 1 minute, there are 200 emissions. Okay, how do we know the emissions? We can actually measure it. We use a detector, and every time it give out emission, we can hear the sound like one tick, like tak, 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 and then you count the sound. You count the sound, you count the number of emissions. Okay, so we use a detector, and that detector we will discuss in the next part. So for now, just that there are three ways we can measure the amount, okay, for the quantity. What quantity it is? This is the quantity that it is talking about. Quantity in terms of mass, in terms of number of atom, in terms of activity. Okay, so let's say we measure this one. There are three ways to measure it. So one of all these three. Then we wait, we let it decay, and it decay into half of the value, meaning that here, sodium. Now, when we measure the mass, the mass become half, 10 gram. The number of atom also become half, 2.5 times 1023. And the activity also become half, 100 per minute. Meaning that initially it was emitting 200 times in 1 minute. Now it become only 100 times. Say that after 8 hours. Okay, after 8 hours, all the quantity become half. And then again, another 8 hours. You take the measurement again, and you find that the mass become, again, half. So 20, 10, half of 10, right? Half of 10 is 5 gram. The Na atom equals to half of this. So half of this is 1.25 times 10, 23. And the activity become half, so it's 50 per minute. Now, the number of atom, this is talking about the sodium atom. Because when the sodium decay, some of the atom will change into a new atom. right? The daughter atom. But here we are only calculating the sodium atom. Okay, the sodium atom is decreasing because some of it is changed into another atom. Okay, the time it takes, how much time it takes every time for it to decrease to half of the quantity? How much time? 8 hours, right? So you wait 8 hours, half of it, and you wait another 8 hours, another half. So we say that the half-life of the decay is 8 hours. Okay, meaning that we say the half-life of this sodium Na is 8 hours. We can write T half equals to 8 hours. That is the meaning of half-life. Again, look at the definition. The half-life of a quantity subject to exponential decay is the time required for the quantity. Time required, okay, for the quantity to decay to half of its initial value. What is exponential decay? Exponential decay means that if you draw a graph, if you have a graph, let's say I measure number of Na atom over time. Okay, you will see that the graph initially, when time is at 0, the initial time, the number of atom is N naught. Okay, so NO. Now, over time, you will see that this decreases like a curved line. Okay, it decreases like, let me draw again. A curved line like this. This we say exponential decrease. It's not going in a straight line. It's going in a curved line, meaning that initially at the start, it decreased very rapidly. But towards the end, the rate slows down. That is why it flattens out here. Okay, all the decay happen like this. I repeat, all the decay happen like this. It is exponential decay. So if they ask you to plot a graph, then you know it should be curving down like this. Okay, now if you calculate, we know that 8 hours, right? 8 hours become half. So meaning that after 8 hours, where is half? Over here. This is N divided by 2. Let me read. NO divided by 2 over here, maybe down a bit over here. Okay, so meaning that this one, this is T1 half-life. Okay, this takes 8 hours here. From here to here, 8 hours. For it to reduce to another half, so half of this one over here, NO divided by 4. Okay, here, then here is another 8 hours. Okay, another 8 hours, and then you can continue. NO divided by 8 divided by 16, all that. So half of it, keep going half. Okay, so the same, all are 8 hours. 8 hours, 8 hours, 8 hours. Okay, so this is the decay. The y-axis can be number of atom. Okay, the number of atom remaining here. Remaining. Sometimes you will see they use y-axis as activity. Okay, it's the same thing, activity, and then they put emission per minute. Okay, emission per minute. Or they can put the mass. Mass over time, over time, over time. Okay, now for half-life, usually they will ask you is calculations. Okay, calculations. We will look at a few examples of how to calculate the half-life of the material. All right, take a snapshot, very quick one. We look at the next page. Example 1. A radioisotope. Radioisotope means it is a radioactive isotope. Okay, radioactive isotope. Because sometimes the atom, the original atom is not radioactive, but its isotope is radioactive, just like the sodium. Okay, sodium 23 is not radioactive, it is stable, but sodium 24 is unstable, it is radioactive. So sometimes the original atom is not radioactive, but the isotope is radioactive, right? So that's why you see a radioisotope has a half-life of 8 hours. Initially, there were 3.6 times 10 to the power 18 radioisotope atoms. So what quantity is this? This is the number of atom, right? You can measure the mass, you could measure activity, but this one is the number of atom. In a sample, how much time is taken for the number of atom to fall to 4.6 times 10 power 17? Okay, very simple. We do very easy calculation. We start with the initial amount. What is the initial amount? 3.6, right? 3.6 times 10 to the power 18 atoms. Starting here, we know that the half-life is 8 hours, right? So we just draw arrow diagram like this. You can follow me. Whenever you do it, you can do it the same way as me. Okay, so we start with the initial one, and then we draw the arrow, meaning that after 8 hours, it become what? Half of this, right? After 8 hours, it becomes half of this, which is 1.8 times 10 to the power of 18. Then you do another arrow. After 8 hours, become what? Half of this again, 0.9 times 10 to the power of 18. Okay, this one I can write it as 9 times 10, 17. Okay, just to put it in standard form. Now, to continue, I draw another arrow, 8 hours, half of this, it would be 9 divided by 2, we get 4.5 times 10 power of 17. Do we stop here? Yes, because the question wants until only 4.5 times 10, 17, right? So the time for it to fall all the way down to 4.5 is 8 hours, 8 hours, 8 hours. So 8 hours times 3, 24 hours. That is 1 day. That is your answer. 1 day, it takes this much, fall all the way down to this one, only 1 day. Okay, so this is a half-life. Example 2. A radioisotope P will decay to nuclide Q by emitting radioactive emission. A sample which initially contained 100% is found to have 3.1% after 3 years. What is the half-life? We start at 100% of P. Okay, one half-life, it goes to what? 50%. Another half-life, it goes to 25%. Another one, 12.5%. Again, 6.25%. One more time, 3.125%. Do we stop here? Yes, 3.1%. From here, 100% decay all the way to 3.125. How many half-life? We got 1, 2, 3, 4, 5. 5 half-lives. So we write 5 T half equals to It says from the question, after 3 years, meaning that from the top all the way to the end, it takes 3 years. So we know that 5 half-life equals to 3 years. Okay, equals to 3 years. We convert it to days first. 3 years is 365 times 3. Okay, so 5t half, 1095, and half-life is equals to, divided by 5, we get 219 days. It takes 219 days for the isotope P to decrease to half of the value. Another 219, half again. Okay, so this is why after the explosion in the Chernobyl, the nuclear reactor explosion, it sends out all the radioactive material in the atmosphere, in the soil, in the river, in the air. All this radioactive material, they have very large half-life. Their half-life is very long. Some goes to a few years, some goes to a few decades. Okay, you wait for a few decades only for the quantity to reduce to half. How many years you want to wait until finished? Many, many decades. That is why radioactive material, they can stay very long in the atmosphere. It's because of the half-life. They have very large half-life. Okay, a few years only decay until half. There's still so much more to decay. So it is still radioactive in that area. Okay, some radioactive material has very small half-life. 1 day, finish. Okay, especially used in the medicine. Okay, they insert radioactive material in the human body. Okay, like they do the scanning lah. Okay, so they insert all this radioactive material has very short half-life. 1 day, 2 day, already gone. Okay, so meaning that short half-life, that means that the emission is not so much. The dose is not so much. Okay, so it won't harm the body. If large half-life, the dose is very high. Okay, you can send out many emissions. All right, so that is what example 1, 2, and we got one more, example 3. This one. A sample of radioisotope of mass 64 has half-life 12 minutes. What is the mass of the isotope after 1 hour? Okay, same thing. We do 64 gram. We know the half-life is 12 minutes. What is the mass after 1 hour? Okay, then 1 half-life, 32 gram. 1 half-life, 16 gram. In the exam, in the SPM, you can do like this also. They won't give you wrong one. Okay, you can do like this. 16 gram and then 8 gram and 4 gram, 2 gram. Okay, all the way down to 2 gram. Okay, we know that this is 12 minutes, 12 minutes, 12 minutes, 12 minutes, and 12 minutes. We count now. How long is 1 hour? Okay, 12 minutes. 1, 2, 3, 4, 5. Exactly 60 minutes. 1 hour. All right, so we stop here. 2 gram is the final mass. But there's one more example I want to show you before I send you the exercise. Give me a second. Okay, look at the screen. Okay, here the diagram shows the radioactive decay series of nucleus P to nucleus S. Sometimes you will be given graph like this. Okay, this one. So you can see starting from P, it decay to Q, decay to R, and decay to S. This is the end product. How many alpha and beta particles are emitted in this decay? Okay, so how do we find it? You can do it like this, right? From P to Q, how many alpha or beta are emitted? You see the nuclear number. P has a nuclear number 26. I write it down here, 26. 216, sorry, not 26, 216. And proton number is 84. Okay, 84. It goes to Q with a nucleon of 212 and a proton of 82. What decay is this? From P to Q? 216 become 212, that's minus 4. 84 to 82, that's 2. So that is 1 alpha, 4, 2. Okay, 1 alpha. Then how about from Q to R? Okay, let's write this down here. Q is 212, 82. To R, it's 212, 84. What decay is this? You see the nucleon does not change, that is beta. Okay, does not change, that is beta. But the proton number 82 goes to 84. If one beta is emitted, that's only plus 1, right? But this one plus 2 means you got 2 beta emitted. Plus electron beta particle, but I put 2. Okay, 2 beta particle are emitted because we can see the proton number plus 2. Here to here is plus 2. Okay, so 2 beta are emitted. For the last one, R to S. Okay, R is 212. Proton number is 84. Goes to S is 208. Proton number is 82. Again, this is another alpha being emitted. Okay, minus 4, minus 2. So total, how many alpha, how many beta? We got 1 alpha, 2 alpha, and we got 2 beta here. 2 beta and 2 alpha. Okay, so this is how you do question like this.